All right, today I will talk about Clifford's theorem, which is a fundamental theorem on the restriction of a representation to a subgroup. So let us begin with finite group. Let's begin with a finite group G and a subgroup H of G. Then suppose phi I from GL of WI, where I runs from 1 to L are the irreducible representations, are the irreducible inequivalent irreducible representations of H, and I assume that they have characters chi I, sorry, they have characters let's say psi I in such a, so now for any irreducible representation V rho of G, we consider the restriction of rho to H. So then it will be so there will be non-negative integers such that this will be d1 up to dl phi L. We prove that then what we must have that summation di square I from 1 up to L is less or equal to the index of H in the index of H in G, and equality occurs if the character of rho vanishes identically on the complement of H in G, is just a set theoretic complement. So this is what we have proved last time. So that shows that given a representation of G, of course irreducible, if we have irreducible representation of G, then in principle there are plenty of choices. There are plenty of choices for D1 up to D2L, so that the restriction of the representation can be written like this. So that shows that if we just restrict and if we just restrict an irreducible representation of G to H, then actually we can't, in general, we can't say much that what it is going to be after restriction to H. So today what we are going to see is the following, that we will see that in the very special case when H is normal in G, then indeed we can say something more, actually a lot. Then what we will see is that in this expression, what we will see is, first of all, the I such that di is non-zero. For all those i's, degree or dimension of phi I will be same. Dimension of phi I will be same. First we will see that. So the inverse, all the sub-representations of all the irreducible sub-representations of this will have the same degree. And furthermore, again, so for all di such that di is 0, or they will be same. All di such that di not equal to 0 will be same. This is what we proved by Clifford's theorem. under the assumption that H is normal in G. Okay, so before we prove Clifford, before we start proving Clifford's theorem, let's make some observations which will be instrumental in the proof of Clifford's theorem. So we assume that let V rho be an irreducible representation of G, and H is normal in G. Okay, and so we will talk about the restriction of rho to H. This is a restriction, this is a representation of H on the same vector space V. Okay, so let W be a subspace of V which is H invariant. Okay, so observation one, it says that for every G in G, so rho G W, this is of course a subspace of W, is G, first of all H invariant and then irreducible, provided if we assume that the W, okay, let's come to the reducibility part later. So first we will prove that rho G W is H invariant, and then furthermore W is irreducible. Remember, is irreducible means that is irreducible in the sense of H invariant. So in this, irreducible here means that it doesn't have any invariant H invariant subspace other than W, and the trivial is irreducible. So as I said here, so the what we mean by this is the representation of H on W is irreducible. Then so is rho GW. This is what we will first see. Okay, so to see this is H invariant for every H in H, rho H, for every H in H, rho H into rho G, rho H, rho GW. So this is basically, this is rho HGW. Okay, and now what is this? We know that H is normal, that is every left coset is same as the right coset. So small hg has to be G times some small h prime. So therefore this will be rho G, rho H prime W, and rho H prime W is nothing but W because W is G H invariant. So thus what we get is rho G W, which shows that this is invariant. So now we shall prove it's irreducible. Now we shall prove the irreducibility thing. Before we prove the reducibility thing, let me again let us again note that what we have proved is whenever W is any H invariant subspace of V, then for every G, rho GV is also H invariant. So we shall use that here. So suppose W prime is an H invariant subspace of rho GW. W prime is an H invariant subspace of rho GW. Now since W prime is H invariant, so from our earlier assumption we can say that rho G inverse on W prime is also going to be an H invariant subspace, and that is contained inside W. So it's a H invariant subspace because we have just made a general observation that for any W and any G, this is what we are going to have. So from view of, so this is a H invariant subspace of W. Therefore, there are only two choices for this: either trivial or whole of W, and that forces either W prime is trivial or rho GW. That shows the irreducibility part. Okay. So this is our first observation. The second observation is the decomposition of V. So in terms of this translations of W, we look at the following sum. Okay, so by its very construction, it is gene variant. Okay, now since it's a gene variant subspace of V, we have two choices for that. Either it is trivial, or it is it is whole of V. So if W we start with is non-trivial, then certainly this is not going to be trivial. So then this has to be whole of V. This has to be whole of V. And once we have this is whole of V, so next what we will see that whether this sum is direct or not. We will see that yes, this sum is direct provided we throw out some redundant summands. So for that we will appeal to a quite general observation. So what we recall is suppose we have a finite dimensional complex representation rho of a finite group G, and W1 up to WL are irreducible subspaces of V, such that V is just their sum. V is their sum. Then so these are all irreducible. So then we will see that there exists a subset of 1 up to L such that V is in fact direct sum of, so that is throwing out some summands which are redundant, we can make this sum direct. This is what we can prove in generality. Let me quickly prove it. So I would rather give a sketch. So what we do is for any fixed I, so we can consider these two things, right? We fix an I, and then we consider the intersection of Wi with the sum of others. This is a subspace of Wi, and in fact a gene variant subspace of Wi, because everything is gene variant. All the Wi's are each of these are a gene. Each of this W1 to Wk is gene variant. So both these are gene variant, and so is their intersection. So therefore, for this, so this is a gene variant subspace of Wi. So it has only two choices: either it is trivial or whole of Wi. So in this later case, what it means is Wi is actually contained in the sum of others. Okay, so keeping that in mind, what we do is we first start this with W1. We'll take W1 and then take the sum of others. Take the sum of others. If W1 is contained in that sum, we will throw out W1. Otherwise, if W1 is not contained there, then in that case the intersection has to be trivial. So we then proceed. Proceed for W2 and perform the same checking. If W2, if the intersection is trivial, then we will go ahead for W3. So that's how we will go. So if it happens that from W1 up to WL, each of them passes the test, that is in the sense that none of them is contained in the sum of others, then indeed this sum will be direct by definition. So if this is not the case, then when we start our checking, then whichever first fails, let's say, 'W3 happens, so W1 and W2 passes means, 'W1 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 and W2 pas if we fix that and take the sum of others, then the intersection is going to be trivial. So whichever first fails, then what we do is we will remove that. Then we will, so once we remove that from the sum, since that is contained in the sum of the other terms, once we remove that term, so the sum still remains V. Then we again start the checking from the beginning. So since we are dealing with only finitely many things, at some after some finitely many steps, we will arrive at a situation where none of the terms present can be none of the terms present is contained in the intersection, contained in the sum of the other terms. So therefore, and in our process, every time whenever we are throwing out a term, the sum, that entire sum is not changing. So therefore, when we stop after finitely many step, our sum will be still V, and since none of the terms present then will going to be contained in the sum of others, so then the sum will be direct. So I just briefly sketch the proof, and in fact this is the proof. So we use that to this situation because each of these terms are H irreducible. Okay, well, it's appropriate to say H irreducible because now what we are doing is V is already irreducible represent. This was already irreducible representation of G. So if we just stick to G, then there is nothing actually. But when we restrict that to H, then only all this comes up. So here irreducible means H irreducible subspaces. So if we just use this observation here, what we get is the following, that there exists a subset of G possibly proper such that V is the direct sum of rho G W, where G lies in S. Okay. So in simple words, V is the direct sum of some rho G W's. All right. Next, what we will see is, let's go to the next page. Next, what we are going to see is namely some isomorphism kind of stuff. So suppose W prime, W and W prime are H invariant subspaces of V, and the sub-representation and the sub-representation of this on rho and rho prime is isomorphic. That is, we have an isomorphism from W to W prime, which is also H invariant. Okay, which is also H invariant. This is if this happens, then for every G, rho G W and rho G W prime is also going to be isomorphic as representations. Let me recall, for the reason for writing H invariance is we want to say that the representation of H, so the sub-representation of this, which is a representation of H on this and on that, and these two representations of H are going to be isomorphic. So how to prove that? For that we have to find out a H invariant linear map, and that's quite easy to do. That's indeed quite easy to do. W prime. So a typical element here, rho G W, rho G W X. So rho G small w goes to rho G phi W. Okay, because phi was a G invariant linear map from W to W prime. Now we will show that this is in fact G linear. For that, let's observe the commutative. So for every H in H, observe that we have the following commutative diagram. Observe that we have the following commutative diagram. Rho G W prime, rho G W prime. How is that defined? So the vertical, both the these two vertical maps are both of them yeah, both of them are exactly this. And here we have rho H. Here also we have rho H. So now we say that this is commutative. How to check that? If start with a typical element here, which is this. So once we apply rho H to that, so rho G W, this goes to rho H G W. Recall that H is some G H dash. Therefore, what we have is rho G H, rho G, rho H dash W. Recall that rho H dash W is in W because W is H invariant. So starting with element here, once we apply rho H, this is what we get. And then next, when we apply the vertical map, it just goes to rho G, because this lies in W, so phi of rho H W. Okay, recall that phi is H invariant, so basically then it will be phi H, rho G, rho H, phi W, right? Rho G, rho H, phi W, sorry, rho H prime, it will be here. Yeah, H prime, and that is what again, rho G H prime, rho H G phi W. Okay, now you see this is so now you see that this is what we are getting in the alternate route, like rho G W. When you apply phi rho H on that, it will be rho H G W. Okay, again let me show you. So here it is rho G W. When you apply the vertical map, it comes to rho G phi W, and once you apply rho H to that, then you should get rho H G phi W. This is what you already had here. So this map is in fact H invariant, and of course it's bijective. Of course, it's bijective because it's a bijective linear map, because so is phi. So therefore, this observation says that once we have two H invariant subspaces, once we have two sub-representations isomorphic, then so is on any translation of them. So is when we translate both of them by the same rho G. Okay, all right. So we are now ready to prove the Clifford's theorem. So as I said, the theorem says that suppose V rho is an irreducible representation of G. V rho is an irreducible representation of G. We can restrict that representation to H. Okay, so once we restrict that to H, then we can write that as the direct sum of the irreducible representations of H, which in the beginning we in the beginning we said that we will throughout use these notations. So therefore this will have the form that from D1 D2 DL DL, okay, and isomorphic to that. Yeah, so here it has to be isomorphic. So yeah, now you see that here some di might be 0. So What are di's? Di is nothing but the number of times phi I occurs in the restriction, right? Number of times it occurs. Okay. So if di is 0, then we simply we don't have any sub-representation of this, which is isomorphic to phi I. So in that case, we say that phi I is not contained in in this restriction of rho. So if di is non-zero, then we will say phi I is contained, and then di is said to be the number of times it is contained. So now the Clifford's theorem say that all the sub-representations. So then let me write it somewhat more formally. Let S be the set of all i's. Let S be the set of all i's such that di is non-zero. Okay, then it is we once we set this S, so then res has to be isomorphic to di phi I is in S, right? So the first conclusion of Clifford's theorem says that then E for all phi i's such that I in S have same dimension, and then the rest says that all di's, again I in S, are same. So in view of that, you can then simply write that res H rho is basically isomorphic to some fixed d times phi I in S. Okay. Yeah. So in words, the first one says that each irreducible sub-representation of the restriction, so all the irreducible sub-representations of the restriction will have same dimension, right? Because when this can be decomposed as a direct sum of irreducible things, the irreducible sub-representation, then it will be, and that direct sum is isomorphic to this. So therefore we see that in the decomposition, all irreducible sub-representations which are all irreducible sub-representations, of course non-trivial, or so in the decomposition we in fact ignore the trivial decomposition, ignore trivial subspaces. So let's forget that. So basically all the irreducible sub-representations of this will have same degree, and any reducible any reducible representation of H, if that is contained in this restriction, then it will contain exactly same number of times as others. So again, let me I should not confuse you. Let me make it more clear. So there could be reducible representations which even that is phi i's which do not even occur, which do not even which are not even contained, which may not even contain may not be contained in this restriction. So the second thing it says that so all the irreducible representations of H which are contained inside this restriction will have same number of occurrences. Sometimes people call it multiplicity. So in that language, it is same as saying that all the irreducible representations of H which are contained inside the restriction are of same multiplicity. Okay, so we will now prove Clifford's theorem. So you see that, so this is under the assumption that H is normally in G. Under the assumption that H is normally in G. So now let's sorry, cancel. So now let's prove that. Yeah. So what I was saying that now the advantage of Clifford's theorem is that when we restrict the what Clifford's theorem says is when we restrict H, restrict the representation to a normal subgroup, then for that your number of choices basically limited. So only those those irreducibles can be contained which have the same degree, and if they are, once they are contained, their multiplicity should be same. So that basically makes the number of possibilities quite limited in this situation. Okay, let's now finish the proof. So the first one says that they have the same degree. So that is quite clear, because if you remember that if W is a subspace of V which is H invariant and H irreducible, again let me remind you, H irreducible means that the subrepresentation of the restriction on W is irreducible, or in other words, this does not have any further proper and non-trivial H invariant subspace. So then we see that V then has to be the direct sum of rho GWs for some just a minute. I think I have used S in both the places, if I'm not wrong. Yeah, so maybe here we can just change it to be some R. You can just change it to be some R. So R be the set such that V is the direct sum of them. And we should remember that each of them being isomorphic to W has dimension same as that of W, and each of them are irreducible. Thus we have a decomposition of V into irreducible subspaces, where all the irreducible subspaces occurring in that decomposition have the same dimension. So this is what is happening in this representation. So here all the irreducible subspaces which are occurring in the decomposition have the same dimension. So once it happens in one decomposition of V into irreducible subspaces, then it must happen in any decomposition of V, because the reason is very simple, that each of this summand is isomorphic to so each of them, so subrepresentation on each of these is isomorphic to some phi I. So that shows that the phi i's which correspond to these, they have the same dimension. So now if you take any other decomposition of V, only those phi i's will occur, because that's what we have proved earlier, that the irreducible representations that are going to occur in a representation of the group that doesn't depend on the choice of the decomposition. So whatever decomposition of V you choose into irreducible subspaces, H irreducible subspaces, only those phi's will occur. Those phi i's will occur, and already we have proved that those phi i's have the same dimension. Hence, in the decomposition of V that you have chosen, that has the property that all the irreducible subspaces occurring there, they are having the same dimension. Okay, so the proof of the first part is clear. We shall now go for the proof of the second part. So the proof of the second part is basically a direct application of to prove the second part, we shall appeal to the canonical decomposition of restriction of rho. So canonical decomposition means V is written, canonical decomposition means V is to be written like this: V1, V2, VL, where each VI is the direct sum of equivalent. Each VI is the direct sum of equivalent subrepresentations, and if we call those subrepresentations as components of VI, and so furthermore, no component of VI is isomorphic to any component of Vj if I not equal to j. This is what we get in the canonical decomposition. That is, first we decompose, and then we put the isomorphic subrepresentations together, so that each Vi is the direct sum of the same irreducible subrepresentation, and no component and no irreducible subrepresentation of Vi is going to be isomorphic to any irreducible subrepresentation of Vj. Okay. Now the reason is, now what we are going to do is following, that we shall look at rho g V for any V. So rho g V is again V, but rho g V at the same time, since V is just the direct sum of them, so rho g V has to be rho g V1, because invertible linear map preserves the direct sum rho g VL. Okay. So now we will see that each rho g Vi is also something which is very interesting. Why? Because each Vi, if you recall, Vi is the direct sum of same. Vi is the direct sum of same. Same means equivalent or isomorphic irreducible subrepresentations. Okay. In fact here, because we have seen that this is going to be in view of this, so then in view of this, what we can just write as Vi will be something like some direct sum of some rho g Wi, so G belongs to, let's say, G belongs to Ri, and R1 up to RL, the index set will be there. Basically, their union will be R. Okay, because once we have this from here, the way to get VIs are basically we just put the isomorphic such summands or subrepresentations together, and when we put them together, we get the components of the canonical decomposition, that is the VIs. So each Vi is of this form. Well, I think I should change the notation. Well, let's write that G prime here. So once we apply rho G V prime, once we apply rho G Vi, then certainly what we should have is so rho G prime W. Now recall that any two terms here are, any two summands here are isomorphic. Okay, So once we apply rho g on both of them, so after then, even then, the subrepresentation on the, so again let me put it in a better way. So any two summands here, uh, any two summands here are isomorphic as subrepresentations of the restriction. So once we apply rho g on them, they will still be isomorphic as subrepresentations because of this. So thus, once we apply rho g on vi, we still get it is a direct sum of equivalent direct sum of isomorphic subrepresentations. And furthermore, if we compare rho g vi, and rho g vj, so no irreducible component here is going to be isomorphic to any irreducible component here, because if some irreducible component of rho g vi is isomorphic as a sub representation of H to some irreducible component of rho g vj, then applying rho g inverse on both of them, we will see that we will get an isomorphic we'll get a component of vi being isomorphic to a component of vj, which is not possible. Thus, our situation is now very interesting. We know that each rho g vi is direct sum of isomorphic subrepresentations, and no component here is going to be isomorphic to any component of any other. No component of a rho g vi is going to be isomorphic to any component of other rho g vj's. So what does that show? Doesn't that show that this is also, so doesn't that show that, because again try to understand, each of these summands are isomorphic, are the direct sum of isomorphic subrepresentations, and there is nothing common. Okay, so doesn't that mean that this is also nothing but the same canonical decomposition, may possibly ordered in a different way, because rho g v is of course v. So this is also the same canonical decomposition of the representation of res h, but possibly the summands are occurring with a different order. So that means what we have is each rho g vi is actually some vj. Okay, is actually some vj. Once it is there, then we see that once we calculate that dimension, so dimension of vj is same as dimension of vi. Okay, right? And what is the dimension of each vi? Remember that each vi is something of this form. So thus dimension of vi is dimension of w times number of elements in Ri. Okay, so dimension of vi is order. So dimension of vi is number in Ri, or number times dimension of w. Okay, so same is here. So that shows that Rj and Ri, they have same number of elements. So what are Rj and Ri? In V, so what is Ri? Ri just number of elements in Ri is nothing but that the number of times this subgroup. So number of times, like if you look here, so the subrepresentation here corresponds, the subrepresentation here is isomorphic to some of this some phi, let's say phi is isomorphic to, let's say, some phi ki. Okay, so thus in Vi we have the total number of occurrences of phi ki. Okay, and now we see that that is same as here in Vj, the total number of occurrences of the corresponding phi kj. So that shows that if rho g Vi, if rho g Vi is Vj, then the irreducible representation which occurs in rho g Vi, the irreducible representation which occurs in Vi, and the irreducible representation which occurs in Vj, both of them occurs in same number of times. Okay, now we are almost done. Now in order to show that in order to complete the argument, what we just have to prove that given any ij, there is a rho g such that rho g, there is a g such that rho g Vi equal to Vj. Okay, so that shows, if we can prove that, that means here every Vi can be transformed to every other Vj. So that means, that shows that the representation, the irreducible representation which occurs in Vi, its number of occurrences is same as the number of occurrences of the irreducible representation in Vj for every other j. Okay, so that's so yeah. Okay, and that's very easy to see because suppose Vi, so now to prove this, let's observe that if Vi has a term, let's say rho gi w plus something something, which I don't care, and Vj has a term rho gj w, then what we do is we multiply. We have to consider rho gi, rho gj gi inverse. You have to just consider this, because you see that once we apply, so once we apply this on Vi, one of these terms becomes this, one of these terms maximum becomes this, and then it forces that rho g Vi has to be Vj, because rho g Vi I know is some other component of some other component here, some other rho g Vi is some other rho g Vi is rho g Vi is some is exactly something from here, and here this here each they do not have anything in common, right? So here once, so after applying here, once we get that rho gj w is containing inside that, so then it has to be Vj, because if it be something else, then rho gj w cannot be contained inside that. So we are done basically. Let me just quickly summarize. So we were supposed to show that in the Clifford's theorem that all the irreducible representations which occur in they occur same number of times. So we did it using the canonical decomposition, because if a representation occurs, then then number of times it occurs, then they will constitute one. They will constitute a Vi in the canonical decomposition. I repeat that if some, let's say some irreducible representation occurs there, then the sub-representations which are isomorphic to that irreducible representation they will come. So once we put them together, they will constitute one summand in the canonical decomposition. So once we can prove that number of sub-representations appearing here, number of sub-representations appearing here is same as the number of sub-representations appearing. So if we can prove that number of sub-representations appearing in one VI is same as the number of sub-representations appearing in, just a minute, sorry, why is this happening? Number of sub-representations appearing in VI is same as the number of sub-representations appearing in any other VJ, then we will be done. So the number of sub-representations appearing in VI is precisely Ri, okay? And then we prove that we have ways to send VI to VJ for any J, and once the image of VI becomes VJ, they have once the image of VI becomes VJ, then in both of them the number of occurrences of the irreducible sub-representations are same. So putting everything together, we proved Clifford's theorem. Okay, so again, Clifford's theorem is under the assumption that rho H is normal in G. If H is normal in G, then we see that by Clifford's theorem that only those irreducible representations are allowed to be occurring, allowed to occur in or in other language allowed to be contained in res rho. Only those who are allowed. Let me just complete. So only those phi i's who have same dimension, they are only allowed to be contained here. And once they occur, so those who will occur, they will occur same number of times. Okay, with that I will stop.